Morning. Uh, Today we'll discuss about linear programming and integer programming. That's our schedule. So this is what we have uh, practiced for your assignment. I hope you still remember, right? So we have a company with two warehouse and two retail shop. Okay, and we know the warehouse has 250 computer A, and for B has 400 computer, while the retail shop need 300 and 200 respectively. Okay, the shipment cost is given like this. Now we want to know how many should we ship from the warehouse to the retail shop for each pair to minimize the total cost, right? So uh, we know this has four decision variables, okay, and then uh, we can organize the data something like this, and then we can solve, right? So uh, we can identify the constraint that the total supplies from the warehouse cannot exceed the capacity, and the total demand for each shop must be equal, okay, and all the numbers here must be non-negative. So once you identify the constraint and the objective, you can decide, yeah, the LP formulation, something like this. Right? Once you can make this linear programming formulation, then you can use any software, okay, to solve this. So one way to solve is to use Minisync. The other way is to use Excel solver. So my question to you, how did you solve that?
I tried using Excel.
Okay, do you want to show me?
Wait.
So, sharing. How did you solve using Excel?
Wait. I just set up my computer, so that's why
Oh,
I forget
okay.
to think.
Okay.
Okay. Um, right.
can share your screen.
Okay. Wait. Oh, I think the file is gone.
Hmm?
Wait, why? There are several file that is gone. Okay. Oh no.
No.
No, no. Hmm. Let me do backup. Oh, because I did it last week. Yeah,
Hmm.
after the last week. Because 3 days ago, my computer cannot be used, so that's why I reset it.
I see.
Um,
Is there any virus or?
yeah, I think so.
Oh, no.
There are several files that already gone though. Okay. Oh, it's gone.
So
And where should I submit it? On Lantera.
I think still in Lentera. You submit in
Okay.
Lentera. Okay.
Because I just like opened the Google Classroom. I forget that this semester you
Okay.
use the,
Lentera, yeah.
yeah, because my other course are using the Google Classroom, so
I
I
see.
just open the Google Classroom.
Uh, Lentera is the same as Moodle. Last time I remember you like Moodle better than Google Classroom, especially for the quiz.
Yeah, yeah, but the Lantera is not that, it's not that good. I guess the interface sometimes it's confusing.
Oh, really?
Yeah,
Is it not the same as Moodle last time that I make?
yeah, not the same.
Oh, Moodle is better.
Yes.
You can give suggestion on improvement of that so that we can accommodate your suggestion. Okay, so I will
Okay.
share my screen, okay, on how you will put that into Excel. Okay. So can you see my screen now? Okay, so first you create a variable. Okay, so,
Mhm.
right? Okay, so here I want to use only two variables. Okay, so here, wait, wait. Here, this is the four variables, right? If we use four variables, so you set up the uh, all the four variables here, okay, and then you set up all the constraint, the left hand side and the right hand side. The one in yellow are the one that you input, right? And then the one in uh, orange and other color are the one you put as formula. Okay. So for example, the minimize z 18 plus multiplied by x a y plus 15 and so on. So you can see the formula is there in C22, right? And then for the constraint in the left hand side, again you use exactly the same as uh, the formula of the optimization. Yeah. So
Mhm.
for example, x a y plus x a z. So you can put there also. And and then you can set up all of this and use solver, right? Here, this is the example. If we use solver, what is my screen sharing? Can you see it? So first you set up the variables. So you can set any value, for example, 0, 0, 0, right? And, and then you set up the formula. So if you look at the formula, this is supposed to be xay plus xaz, right? So then you set up exactly the same as the constraint. And then on the right hand side, you set up the value. This, the one in yellow you need to type, right? So once you set up all these values, and this is the cost given, right? Then you can use solver. Oh, I don't have solver here, so we set the add-ins there. In solver is here. And then you can set up the solver like this, and then we just solve it there. Okay, so this is meaning, this means 0, right? If I put this as a number, so this is 0. So I think you can do this, right? Or you did?
Yeah.
Yeah. Okay. So another trick is actually to use the equation in the constraint here, right? I will show you the constraint. Can you see the constraint here? If you look at the constraint here, x a y plus x a z is less than, right? The same thing with the second constraint is less than, but the third and fourth constraint here is actually equal. Can you see that? So when we have equal constraint, we can use this, okay, to reduce the number of constraints and reduce the number of variables. Because when we set equal, that means we can put this on the right hand side, right? Okay, so we have something like this. Okay. So we can put this in the right hand side. Then we, instead of 4 variables, now you have only 2 variables. Right. So now if you use 2 variables, the same thing, okay, but now this one you set as another variable. The earlier was the third variable and fourth variable. Now you put it as the first variable, okay, and the equation of the second variable. Now you have only 2 variables, which is xay and xaz. Now using 2 variables, of course, you can also solve the same thing, right? Okay. So if you use 2 variables, if you use solver, again, you set up 2 variables, and then now you set up the constraint and the objective function. The objective function will be different, the result, right? But the actual solution will be the same. You can see the actual solution will be the same. Okay. Okay, that are the review of linear programming, okay, which I believe you have learned last semester, right? Now, to enter the actual course of OR2, we will start with what is called integer programming. Okay. So now is the real course of OR2. Okay. So what is integer programming? What's the difference between integer programming and linear programming? Right? That's the most important part there. So any problem that we have, sometimes we can see that this problem actually discrete or integer in nature. Okay? They are not real number and not fraction. Okay? For example, the number of workers in the scheduling, okay, or the number of airplanes, okay, in the purchase of optimal number of airplanes, for example, or some of the, for example, you want to select project, okay, of course, this become binary decision, yes or no, okay, some project will be selected or not selected, right? So these are example of problem that are integer in nature. Okay, so can you give me one or two example of uh, example of problem then that variables are integer in nature?
Integer.
Hmm.
Mm, the, like um, is this good? This good company.
Something that you cannot define. Think about the variable first. What unit that you cannot divide into continuous real number? For example, you want to find the number of people, right? The number of workers. So of course you cannot have half worker, right?
Yeah, yeah.
Right. Okay. For example, you want to find the number of cars. So you cannot get half car. So they are discrete in nature. So if it is time, then you can put it into continuous. Right? But if there are certain things that actually discrete in nature. Can you give me any other example? What do you want to find that is discrete in nature?
Something that cannot be half is cannot be half. Multiple and the references.
Any example that you can think of?
Each is continuous, right? The
Pardon?
age is continuous, right? So
Age
it
is
cannot be
continuous, yes. Age is continuous.
uh
Time is continuous. Something that is
mm,
great that you cannot define.
divide person. Okay. And half. Mm.
Anything that that you can think of, any variable that you think it's discrete and cannot be defined.
House. All the house.
No? What?
House. A house.
A house, yes. So if you want to find the number of houses, for example, right? You cannot
Yeah,
define. Very good.
house,
What else? One more.
car.
Car, right?
Yeah.
Right. So if you want to find those things, you cannot define. Now, what is integer programming? So IP or integer programming, okay, is basically linear programming where okay, some or all. So important here is the word some or all. Okay, of the variables are non-negative integers. Okay, so see, if all variables are integer, this is called pure integer programming. Okay? So in this case, all variable must be uh, example, yeah, all variable must be equal to 0 or 1. So this is called pure binary, right? Or 0, 1 IP. Okay? If some, instead of all, if some of the variable are integer, we call this mixed IP. Okay? So other name of this is integer linear programming. So basically this is linear programming, but
Mhm.
some or all of the variables are integer. Why this is separated? So for user, if you want to use only, okay, say you use the software, there is not so much different actually. You just set as integer, that is okay, right? But inside the algorithm, they are so much different, okay? Because the matrix of integer usually you cannot solve using the simplex method. Okay, so the algorithm are totally different. So then they created a different name for this. Okay, but for you, uh, if you are just want to use, okay, actually there is not so much different. Okay, so this is an example of pure IP. Okay, so for example, you want to maximize 3x1 plus 2x2 subject to constraint of x1 plus x2 less than 6, for example. And then what to make it pure IP is this line that 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 in x1 and x2 are integer. Okay, without this line, this is linear programming, right? And how to see that this is mixed IP? Again, the one that make it mixed IP is this one, this line. Okay, that x1 is an integer. Okay, while the x2 is not required to be integer. So when you have some of the variables is actually integer and some are not, then you will see this is a mixed integer programming. Okay. Okay. As a practice, can you set this in your Excel and then you show me? Show me three things. Huh? One is linear programming. Second is pure IP. Third is mixed IP. Yeah? Something like this. Can you set up? This is very simple.
Okay.
Okay. Okay. You share your screen. Huh?
Let
So try to solve using linear programming. You want to share your screen? Oh, okay. Set a new blank workbook.
Wait, I have to. Can you see my screen now?
Yeah, I can see your screen.
It is Excel, right?
It is in Excel, yeah, but still beginning.
Okay, so we're gonna make the let me this question is that we just make it better. Let me screen. Yeah.
Mm-hmm.
This one so I can see the question. So
So you have two
yeah.
variables, x1 and x2.
Let's see.
Mm-hmm.
One,
Plus
two,
x2.
x2.
Mm-hmm.
And then
x1 plus x2 is less than 6.
x1 plus x2 is less than equal
To 6.
and then x1 to
x2 is larger than 0.
0.
Okay. That one first. So that is linear programming.
Yeah.
Okay.
Mm-hmm.
So you created two variables, x1 and x2.
Okay. And then we,
Okay.
after this, we're gonna what?
Yeah. You type x1 and then x2 somewhere else. So
Um,
okay, there x1 and then
x2
x2, correct, and then put color any number there, 0 or 0, for example, 0
0
0,
0.
yeah, and put color yellow so that you know this is the one that. Okay, and you if you want you can give name in
Here.
C5. Yes, x underscore 1. Yes, and then the other one is x underscore 2.
Okay.
Okay, very good. So then you calculate the z. Right? Below that, you can put.
Oh, yeah. Wait. Yeah.
Yeah, yeah.
So
So you type z,
C is
and then in C8 you equal 3 multiplied by
E.
3
3
multiplied
multiplied
by
by the 1
x1, yes, plus
plus 2.
2 multiplied by that x2. Very good. All right. And then now you create a constraint. Okay. Now
And the constant is 6.
that one is 6. Maybe it's better if you distinguish constraints or you put left hand side and right hand side. So you put
Mm-hmm.
L it's S and R it S. So
here.
yes, LHS. Okay. So what is that? That
Like
one is
this.
x. No, x1 plus x1 plus x2, right? That one.
This
That
one
one
is
is the
like this.
correct.
Here.
Okay,
Hmm?
enter. And then what is the sign? In column D9, you can put the sign
Oh,
just
like
to,
this.
okay, and then in that one is the right hand side. So
This.
6, correct. So that now you can use solver
Mm.
in data
It,
tab
so,
solver.
there.
Mhm.
So the objective
So
function is this,
set the objective
and
function
then
is
we
C, yeah, and then maximize,
mm,
right? And then the variables is C5 and C6.
so
Okay, and then the constraint
this one
is
is
that
equals
one less
to
than E9.
6.
Very good. Finish that one.
Okay.
Okay, and then so
Um, this one is
yes.
okay.
Okay, you get the result. Okay.
Yeah.
So can you put that result, you copy and paste as value the result in somewhere. So you can put this as LP.
This
Uh,
one, right?
no, only a C5,
Only
C6.
this
Yeah, okay, only that one. So you copy as value somewhere, right?
one here. Okay.
Okay. So now, how do you set as integer programming? So this is uh, easy, but how do you set this as integer programming?
Mm, this
So
is
for example, of course, in this example, very easy because the result is already integer, right?
mm,
Uh-huh. But
so
if suppose you want to set up that this is like integer programming, instead of using linear programming, you want to tell, oh, only x1 and x2 are integer. How do you do that?
all x to
Okay, again, you go to data solver.
mm,
Okay, you add. Now you add. Okay, and then cell reference of C5 and C6 again, the integer, both of them. Okay, that one you change to integer. There you click OK. Okay, and then you solve. See, you got the same result.
yeah, it's the same.
Yeah, in this example, of course, you get the same result because even in linear programming, you already have uh, integer, the result, right? Okay, to show you the difference, let's solve the next problem in the slide.
The
Can
next problem.
you see the next problem in the slide? That is in the slide is LP relaxation. I will show you this one. Wait, I will show this one. Can you see the? So in here you have to maximize z, yeah, 2x1 plus 3x2, but now the constraint is clearly not integer. So x1 plus 3x2 less than 8.25, and then 2.5 x1 plus x2 is less than 8.75. Okay, So, and then both of them now, x1 and x2 are integer. And then you compare with the xp relaxation, with this x1 and x2 are not integer. Okay, can you try it? Similar. Okay, can you share your screen and then do it again?
Okay.
Okay.
I
So
will
can
share my
you
screen.
share your screen and then we do that LP relaxation?
Okay, I will.
Okay.
Yes. Can you see my screen
Okay.
now?
You can create a new sheet if you want, or
Mm-hmm.
you can use that the same thing. Okay. Anyway, so let's do a LP relaxation. So that means, uh, can you go to the next slide? LP relaxation. I think slide number,
Oh, which one?
yeah, yeah.
Number
Slide number
10.
10. Yeah, slide number 10.
This one, right? Can you
Yes,
see it?
yes, yes. So this is similar to the earlier, right? But now you need to put the constraint is a little bit different. Now you have two constraints with
Ah,
is clearly not
yes.
integer. So let's write it
So,
down. So maximize the z.
oh yeah.
So that you
Max C to x1
plus
plus
3x2.
x2.
Mhm.
And
Okay.
then substitute the
Okay. Check the
constant
constraint.
x1 plus 3x2
Less than equal
is then equal
8.25.
25.
Okay. And then the next one is 2
2.x1
x1 plus x2
x2
less than equal 8.75.
okay, and the last one is x2
Yeah, that is larger than
is larger than 0.
0. Yeah, okay. That is okay.
Okay,
Okay.
so
So let's do this first.
so C.
Z.
It's the same, right? For the C.
X1, X2 first.
Oh, wait, I will rename
You create the variable
the
first.
x1 to
Yeah, X1 and
one,
X2. Okay,
and
and
then
then
Z.
Z. And then
X1 is
you can put 0, no
the red,
problem.
red number, right?
Right. And then put yellow so that you know this is the one that you will find later.
X. Yeah, yellow, yellow. Okay,
Okay.
and then this
And
one
then
is
do you
2.
want to put name so that you will not confuse?
Oh, yeah.
That's easier, right? So that one is x underscore 1. Uh, uh, the name should be, because you have two seats, so now you need to go to the formula, okay, and then define the name. New one,
Then you, oh,
right? That's okay. X1 underscore 1 is okay, but the scope is in the not in the workbook, but in that sheet.
shit.
Yes. Click OK.
Okay.
Okay, and then next one, new one again. Again the same, X2, right? Oh, no, 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 no. The next one is B7. You
Yeah.
go to B7. Okay. And then new X2 underscore 2. The scope,
This
don't forget. Yes. Scope. Yeah. Okay, good. Close it. Now you can start to create the z, which is 2 multiplied by x1 plus 3 multiplied by x2. Right. Very good. Okay. And then now the first constraint. So, okay, you just type constraint here. So, first constraint. Okay.
Constraint. Yes.
Yes. Okay, so that one is equal of
Equal
x1
x1
plus
plus
3
3
multiplied by x2.
2
Enter.
and then
And then less than, that one
2
is 8.25.
5
Okay, the next constraint is
2.5
2.5 multiplied by
multiplied by x1
x1 plus
plus
x2.
x2
Enter.
and then
That one is the same.
equal to 8.75.
8.75. Okay. Now you can try to solve using linear programming. Right, in data solver.
This one is the same with the last one. So
No, solver.
solver set the objective is this one.
C, yes. And then
Then maximize
variable
variable
is
is this
2,
one.
correct. And
And
then
then
add.
the
Now you have to constraint that one less
and
than
this
that.
one.
Okay, add the second on that one less than the second constraint.
Okay.
Oh, great. Now you solve it, you get the result. Now you copy that result, x1, x2, and z somewhere, so that you can compare later. Okay, let's copy as space value. Okay, that is the LP solution, right? Now,
Oh,
yeah, that of course this is not integer, right? Now, what happen if we set that x1 and x2 must be integer? So you
oh,
go to solver again. So what you will
add
do, you will add, right? So
the
the x1 and
x1
x2,
x2.
correct. X1
So
integer,
means that
add. The second one
this one
also integer.
is
Okay.
okay.
Okay, so
Okay.
yeah,
Oh, this one is
okay.
changing.
Oh, that one is also changing. Oh, because the earlier you did not copy and paste as value.
Ah, yeah. Wait, let me change it to be here. Okay.
Okay. Now you can see the difference, right?
Okay.
Okay. So if you use integer, okay, the result is 2 and 2, right? And then the z is less than the z of real number, right?
Yeah.
Yeah. Okay. So, but the x1, the x2 is actually larger than the x2 of linear programming. Okay. You see that? The x2 in linear programming is 1.8, correct? But the in IP going up, not going down. Okay. So now let's compare that in the next slide.
The next one.
Yeah, if you look at the next slide, you will see. Okay, I will just show you.
Okay.
Okay, in this slide, you will see actual LP is this line, right? This is the line that define the linear programming, right? Correct? This is the, so when you said, I want to set up as integer programming, so they are not using this value, okay? Usually the result is in this value, right? Right? So the result in integer programming is the integer. It is, I will put different color, green. So this one. This is the feasible solution of integer programming. See? Can you see that? Okay. LP solution is the corner. Okay. But integer programming is the integer. And then we will find the closest, the one that produce the maximum value. Okay. So the relationship between optimal integer programming and the optimal LP, the linear programming relaxation. Yeah. So you will see that the objective function, okay, value of the optimal IP can never be better than the objective function of the optimal LP relaxation. Okay. So of course, for maximization, so it is the upper bound. If for minimization, this is the lower bound, right? So now if we found the optimal IP, then you know that the objective value must be lower than the LP relaxation. Okay. So this is if then, not then if, okay? Can you get it? You will see in your example earlier, right? The LP itself, how much? The objective function, the Z. You are still mute.
For the first question or the second?
The second question.
So the first, if we use linear programming is 11 point.
Yeah, 11 point something, right? And then if you use integer programming, you get
10.
10, right? So that means what we are saying here in this slide is saying that, look, if you use integer programming, okay, maximum, right? In this case, so you cannot go beyond 11 point something above. It must be less than 11. Do you get it? Okay. If the IP, okay, cannot be better than the LP. Okay. So 11.25, right? It cannot become 12. Okay. Can become 11, can become 10, but cannot become 12. You got it?
Yeah.
Okay. So yeah, this is called bounding optimality. Yeah. So then your next question probably, hey, if I know the LP, okay, can we just get the integer solution of the LP? Yes or no? Okay. Can you share your screen again on your solution? Your solution a while ago was 2.7 and 1.82, right? For the LP, this one. So can we just make it into integer? For example, 2.7 become 3 and then 1.8 become 2. Is it possible to become the result of integer programming?
I think
No.
It will be no, right?
No. Yeah. Why not? That's the question, right? The question is why not? Okay. Because the truncate or rounding up or down may lead to the invisible region. Okay. So even if it is within the visible region, so there is no guarantee that this is actually the optimal solution. So this is an example. Okay, I will give you example. Let me share my screen of this example. You see, in this example, okay, if you put, you see that this is the actual LP, right? This is the boundary of the LP, okay? And then this is the integer the only integer solution that you get, okay? Then you will say, okay, what if I make it less than that? If you put it less than that, you will get invisible, right? The same thing if you put it larger than that, again, you get invisible solution. So rounding off, okay, will actually create invisible region in this example. Huh? So then the next question is, why do we need IP? Right? Uh, the reason is actually inside the program. Yeah? The integer programming algorithmically is more difficult to solve than linear programming. Okay? Why? Because of the combinatorial explosion. Okay? There are some problem that is so large, okay, with the large variable actually unsolvable. Okay? In terms of algorithm, this is called NP-hard, NP-complete. Okay? They are unsolvable. So if your number of variable is very big, they cannot be solved. Okay? So you can check what is the meaning of NP, NP-hard, NP-complete. Okay? And then you can also search in Google unsolvable problem in computer science. So why do you think they are unsolvable?
Hmm. Because
Can you search in Google unsolvable problem in computer science?
unsolvable.
Problem in computer science. Why do you think they are unsolvable? So
Bukan. Hmm.
okay, there are some problems that can be solved using what is called polynomial time. For example, a linear time or quadratic time or cubic time. Okay? But there are some problems that actually unsolvable because they are factorial time to solve. That means the
No solution.
yes, if the number of the size, yeah, for example, the size of decision value variable is very large, they cannot be solved. That's why there are many heuristic solution or meta heuristic solution because the number of variables is very large, okay, then you cannot solve using just simple method. Okay. So there is a problem called NP hard. Okay. When this problem can be translated into one of the solving any NP problem. Okay. And NP hard is called at least as hard as any NP problem. What is NP problem? Okay, NP problem is non-deterministic polynomial time. That is solvable by polynomial time, but non-deterministic. Okay, there is also a problem is called NP complete. Okay, which is a problem which is called NP. Okay, and NP hard, which is both of them. Example of this problem is called we already discussed or before. Do you remember traveling salesman problem?
Yeah.
Yeah. So that one is NP hard problem.
Oh.
So I think you can only solve when the number of cities is only less than 25. Okay. If larger than 25, you cannot solve optimally. But there are certain algorithms that can solve up to several hundred or several thousands. Okay. In fact, later we will discuss about this. There are some competition worldwide to solve the TSP, the traveling salesman problem. Okay, so this is the time analysis algorithm. You can see here. I think we discussed this in programming, remember?
Oh, yeah.
Yeah. Okay, so there are some problem like the factorial here. Okay, if larger than 25, even if 25n, it's take millennium to solve it, right? So if the problem is only 10 cities, for example, in TSP, you can solve it in 3.6 seconds, but in 25, you cannot solve it anymore. Okay, so again, factorial or exponential, okay, something like this, you cannot solve. So when the problem is actually only a polynomial time, you can solve. Okay. But even in polynomial and your, for example, decision value is actually 1 million, again, you cannot solve the number of variables. In the real industrial problem, sometimes your decision variables can go up to 1 million, in the big problem. So in that case, you need very powerful tools to solve this kind of problem. Okay. Now, if your problem is actually binary, okay, then we can also use IP. Okay. In Excel, you just set it as binary. Instead of integer, you can put as binary. Okay.
The result will be different or not?
Of course, the result will be different. It's either 0 or 1. The X is either 0 or 1.
Wait, let me try it.
Okay, so binary decision, 1 usually mean yes, 0 mean no. For example, something like this. Do you want to build a factory in certain city, for example, in Los Angeles, or do you want to build factory in San Francisco? Do you want to build a warehouse in Los Angeles and in San Francisco? Yes or no? Then you have 4 variables here. Okay, that variable represent decision, right? Yes or no. But yes mean you will build, No means you don't build. Is it clear or not?
Yeah.
So there are some constraints that you can also set, okay, as OR constraint. Okay, so for example, we want to ensure that at least one of the constraint is satisfied. Okay, so if you want to say, look, I don't want both of the constraints satisfied, I just want one of the constraints satisfied. Then how do you do that? Okay, you can do that by creating this type of constraint. You see, binary. Okay, so you create a new variable called y. Okay, and then you will say f is less than m times y instead of 0. Okay, you set it as f now become less than or equal to m times y, and then g is m times 1 minus y. So m, you can choose any number which is very big, okay, to ensure that when f is less than m and g is less than m, they will satisfy both constraints. Okay. Another method, again, you can, if you want to say, oh, what if I want that, ensure that if this one, then this one. So there are some constraints that actually you can set as if then constraint. Okay. Again, you can set up this if then constraint into 0 and 1 variable. Okay, by setting up that minus g, okay, less than my, and then f here is less than m multiplied by 1 minus y. Okay, so y again is 0, 1 variable. So, and then m is again large variable. Okay, using this technique, you can solve various type of constraint. Okay? One is OR constraint, the second one is if-then constraint. Another example of IP usage, integer programming. Suppose you want to have a linear function like this, piecewise linear function like this. Okay? Say you have certain breakpoint. So your constraint is not linear, your constraint is actually piecewise linear. Okay, so if you have a piecewise linear function, okay, then you can set up piecewise linear as 0, 1. Okay, so the piecewise linear usually have breakpoint, right? This is the breakpoint. Okay. Then say I will call this P1, P2 until Pn. Say P1, Pn is this value, right? So, and then say whenever f occur in the optimization problem, now you replace the f is the piecewise linear function, by this function. Okay, so now you set up as a linear, piecewise linear function. Then you add additional constraint. Okay, so you set up the additional constraint to the problem. Okay, the z now z1 must be less than y1, z2 must be less than y1 plus y2, and so on. Okay, and then the y itself is less than, the sum of y is equal to 1, the sum of z is equal to 1, and then x now is a linear function, linear combination function. and then the y is actually 0 and 1. So this is how you will solve constraint with piecewise linear function. Okay. So another application of IP is traveling salesman and knapsack. Okay. Before we go there, do you want to stop for a while? And probably you want to. Okay. Welcome back. Okay. So here it is. If you have several problem, yeah, which is discrete in nature, right? Then you want to assign, okay,
Mm-hmm.
so that this discrete values will become binary. How do you do that?
The discrete.
Okay, for example,
Mm-hmm.
uh, you have gender. Gender is male and female, right? They are discrete.
Yeah.
Okay. Uh, Now I want to put this value as binary. Of course, you can put it as 0, 1. That is okay, right? But how about
Mm-hmm.
if I have 3? For example, I have apple, banana, cherry.
Mm-hmm.
How do you put that as a binary? So you cannot put 0, 1, and then how about this, that the last one? How about if we have 5 values? For example, red, orange, yellow, green, and blue, for example. So how do you set those value into binary?
So we have to mm. um
Any idea?
mm, so we have more than two, right?
Correct. So
Okay.
I have two methods, okay? I have two methods to solve that problem, okay? Let me show you in the slide, okay? Number one, okay, is to assign its discrete value into one binary variable. Okay. Method two is to assign its discrete value, okay, into several
Mhm.
binary variable. Okay. So let us see the first method. So if you assign one to one, right? So one discrete value you will assign as one variable binary. So in that case, if you have 5 values, for example, red, orange, right, yellow, blue, and green, so how many binary variable you will have? 5, because 1 to 1, right? So
Yeah.
each of these binary variable, okay, will have value of either 0 or 1. So exist or not exist, right? So
Mm-hmm.
So in this case, the interpretation is easy. For example, first variable is red, right? So the meaning of exists red or not exists red. Okay? The second variable is, for example, yellow. So that means exists yellow or not yellow, right? Exists or not exists. The interpretation is easy. But if you have many discrete value, so the negative here is uh, the number of variables become so many, right? Is combinatorially explosion, combinatorial explosion. So remember, the more variable that you have, okay, then you will have a bigger problem because of the algorithm to handle. Cannot solve very big problem, right? So this is another example. Okay, yes and no. Build factory in Los Angeles, build factory in San Francisco, and so on. So for each variable value, you assign as yes or no. Okay. So this is another example here. Can you see it? Now suppose I have a table of three subjects. Okay. Name Alex, Brian, and Cherry. Alex is male and will choose pass. Brian is male, will choose fun. Cherry is female, will choose pass. Okay. Then I need to assign this as coordinate. Okay. The coordinate is gender and mode. Right. So in that case, if you assign 1 to 1, what will happen is the gender you will assign, because gender is only two value, right? 0 and 1. So you can say, okay, 0 mean male, 1 mean female, okay, or the other way around, is up to you. Huh? And then now the mode has still three value, right? So in here, example, the three value are bus, train, and fun. Okay. Now for each value, you will assign as 0 and 1. So in this case, bus, the value will be 1, 0, 0. Fun will become 0, 0, 1. Train will become what?
0, 1, 0.
Wow, super. You understand that. Okay? Super. Okay, now the second method is to assign several binary variables. Okay? To do this, you need to decide first, okay, how many binary variables that you need to get, right? So in that case, that depends on the number of values. Okay. So for example, the number of value is C, right? Then what you will do is you get the log of C divided by the log of 2. Okay. This will become the number of, we call it dummy variable. Yeah? dv in here is dummy variable. And then you take the ceiling. Ceiling is round up integer away from 0. Okay. The assignment is arbitrary, but you need to be consistent. Okay. And then the good thing here is you will set into less number of variables. Okay. But the assignment will become more complicated. Okay. Let's take example. Okay. Again, a while ago, we used mode of public transportation to go to school is bus, train, and fun. You have three states, right? Okay. So, and then the number of dummy variable is log 3 divided by log 2. Okay. You remember this is the formula a while ago. Log C divided by log 2. Right? Why 2? Because it's binary. Okay. And then log 3 divided by log 2 is 1.58. You take the ceiling, so you get the integer, okay, is practically round up. Yeah? So round up of 1.58 is 2, right? So now you have two dummy variable. Let's call this dv1 and dv2, right? So then you can assign anything. For example, dv1 is 110. dv2 is 101, right? So then you will say bus is 11, train is 10, fun is 01. Okay. So the assignment again is arbitrary. So for example, you can say, oh, train is actually 00. That's okay, right? So you can represent any coordinate, okay, of its value here. Okay.
The result of the dummy variable must be rounded up.
The result, no. This is the number of variable, the number of dummy variable. This one. dv here is the number of dummy variables. For example, if you have a 5 color, what is the value? How many value? How many dummy variable you will use? 5 color. So you will 5 color will be log 5 divided by log 2. Okay, and then you take the ceiling. Oh, what is that? Can you calculate what is the log 5 divided by log 2?
Log 2 is wait. 5
So if we use
log 2.
Excel,
2.3.
okay, so this one is log 5, okay, log 10 of 5, right? Divided by log 10 of 2, 2 point something, right? And then you put the ceiling, okay, the ceiling math is okay, of this one, okay, you get 3, right? That means if you have 5 color,
I cannot see your, what are
you cannot see my, Excel.
Okay, I see it now.
Okay, can you see it?
Yeah.
Okay, now if you have a 5 color, for example, red, what color you like? Yellow, blue, green, and purple. Okay, 5 color, right? This is 5, right? So then you have 3 dummy variable, dv1, dv2, dv3. Then red, you assign us what? Example.
For example, 1.
Okay, so 111. Okay, red is 111. And then yellow is
011.
okay, 011. That's fine. And then blue.
101.
Okay, 101. Okay, and then green.
011.
001. Okay, and then purple.
000.
000. Okay, it's fine. Okay, you can assign anything arbitrary as long as they are unique. They are not the same, right? No rows are the same. So the number of variable, this is the one that is important here. Right? So again, if you have, for example, okay, number of variable, number of value, number of values is 20. Oh, if you have 100 values, okay, 100 colors. So how many variable you will set?
100 color. So log
So
100
you will get
log.
Okay, log 10 of this 100
7
divided by log 10 of 2, right? Oh, 7, correct. See, instead of 100 binary variable, you only need 7. So you save a lot in terms of number of variables, right? So the more values using the second method, the more value that you have, you save a lot of number of variables. Remember, why you need to save a number of variables? Because larger number of variables mean computationally become invisible. Okay, is it clear now?
Yeah,
okay.
It's clear now.
Next, DV is very smart. So now I have the same as before. Okay. So then I assign bus is 1, train is 10, and fun is 01, right? Then, oh yeah, this one. So then now the coordinate change. Okay. So Alex is now 0 and then 1. Brian is 0 and then 01. Cherry is 1. Is it clear in here?
Yeah, it's clear.
Right. So now we can change this value. We can change this coordinate, but as long as you are making it consistent. Yeah. Right. So this coordinate you can change. For example, instead of fun, instead of 01, now you can change it to 00. That's okay. Right. So the number of variables matter here. Okay, so now if you have 52, practice, say for example, A to Z and then small a to Z. Oh, how many variables? If you use one-to-one method, how many variables do you use? What are they? If you use one-to-many method, how many variables that you use? And what are they? Practice.
Okay, wait.
You can share your screen.
But can you just share the question again? Because
Okay, the question
I
again.
think I
The
don't have
question
the
is actually in
question.
the slide. Uh, Page 31. Okay, I will share it again.
Oh, 221. Oh, okay. I will open it. Yeah. So I will share
Okay, you can share your screen.
if you are using. Okay, I will share my screen. Yes. Wait, the question is here. How many can we for? Easy. Okay.
Yeah, if you use one-to-one
So
method,
for the one-to-one method,
if you want
so
one-to-one
there
method,
is
52 values. So
log 52.
yeah, you use 52 variables, right? Because one-to-one.
Yeah.
What are they? Exactly that. A to Z and then small a to Z.
Yeah.
One-to-one is easy to interpret, okay? But how about if one-to-many? The second method a while ago.
Or the one that used the log, the
Yes,
dummy variable. Yeah.
correct.
So log 52, right?
Correct. So we will have
52
log 52.
divided by log 2.
Correct.
So it's 5.7, so 6.
Yes.
So 6. So if we only use 6, what should we use?
It's up to you now how do you use it. Right? So from 52, now you need to assign. Capital A is what?
Wait, for example, like capital A. Yes.
So you can put DV1, DV2, DV3, DV4, DV5, or X1, X2, X2. It's up to you. That is the actual,
DV1,
okay. DV2,
DV2, DV,
DV3,
DV4,
DV4, DV5.
DV5, DV6. Oh, wait,
Oh,
that's it. 5. Okay.
okay, and then that's the
So,
value A, for example, capital A.
hey, let's like
Okay,
0.
if
Okay,
you want,
this.
if you have so many like this,
Mhm.
you try to make it systematic. For example, you start with 000, and then,
Mhm. Oh, okay.
okay, otherwise you will get a problem if you assign
For
arbitrarily.
this one,
Okay, B,
we
for example, B, and then it now becomes 0, 0, all except the last one is
until
1. Okay, 0 again, and then that one is 1. And then
mhm.
C is what?
Six,
0,
zero,
0, 0,
four,
0. That one
one,
is 1,
one.
0. 1,
Oh,
1,
yeah, one.
1, 0 first, right? And then 1, 1.
Mm,
D now become 1, 1, and so on.
one. Hmm? This
Hmm.
one is
Yes.
this one is 0, right?
0, 0, 0, 0, and then now become 1,
One.
1.
Mm. Oh,
Oh, okay, and then continue. So this is basically
yeah,
binary, right?
yeah.
Binary number of 6 digits. So you can see here, this is actually 0, 1, 2, and so on. So in
Mm.
that case, you can actually create programmatically. To assign this, you can assign using program.
Okay.
Okay, you don't need to manually assign.
Okay.
Okay,
Mm.
okay, good. So do you know how to assign this automatically using Excel?
Not yet.
Not yet. You put that to binary. You can try to. You can set value, yeah, to binary.
All of the sound.
Hmm. So this is my example,
Mm-hmm.
right? So you can set, for example, uh, this is A, right? A
Mm-hmm.
is 0, right? And then B is what? B is 1. That means 0, 0, 0, 0, 1, right? And then C is 0, 0, 0, 0, 1, 0, and so on.
Mm-hmm.
Or you can set all 0, 0, 0, okay? And then this is the one that you can assign. Of course, if you have small z here, that will have 6 value. So you can use decimal to bin.
Decimal. Mm.
You can use decimal to bin. 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 You
decimal 2.
Yeah.
Wow.
Okay, so when you have decimal to bin, you will have this is the actual value. Of course, the one in zero here, you can set it zero mean six zeros, right?
Mm.
One here is 0, 0, 0, 0, and then one, right? Five zero in front and then one. Okay, and continue.
Okay.
Okay, okay, clear. Next,
Yeah.
once you can create that, okay, okay. Now the last part here is to practice 01 IP, just to make sure. So the last slide in slide 44. Can you solve that?
Oh, we will use the IP, right?
Correct.
Yeah. Okay.
Oh, you cannot use anything else because this is binary,
Oh, yeah.
right?
Mm.
So the one that make it IP is the last row of the constraint. Okay.
Mhm. Maximal C equal
Maximizing
to
z x1 minus x2.
mhm.
Mhm. Oh, you want to try using linear programming first before you use IP?
Mm, yeah.
Okay, let's
Okay, I
try.
will try it.
Okay, that's curiosity, right? Okay, you can share your screen.
The result will be different, right?
I don't know. I also don't know. So
Uh,
depending on the problems, right?
mm, so this one is this one, and then x1, x2 equal to 0. Um, equal to 0.
You want to share your screen?
Okay. Wait. Um, that was just my screen. This one.
Okay, that one. X1 plus 2x2, 2x1 minus
So x1
so
and x2.
x1, x2. Oh,
Um,
you're expert
so
already. So you can put any
uh, 1 and then
and
2.
1 and 1. Okay, let's try a
Uh,
1 and 2. What will happen?
and then x1.
Okay. And then that one is underscore x2.
X
Okay. And then
equals
z. Mhm. Which
yeah, the
is
C is
x1
x1 minus
minus x2. Okay. And then the
mm,
two constraint. So constraint
oh yeah, the constant is 0.
is equal.
Wait, where should I write?
Just type it as constraint so
Mm,
that you will know this is the constraint.
here. Let constraint. So the first constraint is this one.
Equal x1 plus 2 2
x1 plus
plus
2.
2 multiply
x2
2. Yes. And then
it should
one is less than equal to 2. Okay. Next,
then
2
next one is 2
equal to multiplied by x1 minus x2. Okay, the copy the up above 1. Okay, let's try first using the what is that? Linear programming. What will happen?
Okay.
You want to put x1, x2 in yellow so that you will know this is the one that.
Oh yeah, I forget. Yellow.
Okay. Yeah. Okay.
And then we go to the software. So this one is the
objective is maximize z. No, z is a B8.
Oh. Wait. This one is B8.
I think you mistyped. Okay. Changing is B6 and 7, correct? Okay. And then add constraint, the first constraint, that one. B5, yeah, B10 less than 2. Okay. Add. Second one less than second one. Okay. Okay. Okay, let's solve this first before adding additional constant binary. Oh, you got the result. Oh, the result is 0.5 and 0. You want to copy?
Copy as value.
Yes. Now, of course, when you set as binary, that will be different.
Okay, wait. Data solver. So add.
Okay. Before changing to as binary, can we set as integer? What will happen?
Okay. So here will be integer.
Okay. Second one is also integer.
Integer.
Okay. Okay, and so
0, 0.
The solution is 0, 0. Okay. Copy again.
Okay.
And then the last one. You change that integer to binary.
Okay. And then this one.
Also change to binary.
Binary. Okay.
Okay.
So
wait, you get the same result. Okay. Let's try that. Yeah. Now x1 and x2, now you set as initial value different. For example, 1, 1. What will happen?
1, 1.
Yes, and then solve again. Will we get the same result or not?
For the binary?
It's okay.
Or all of it?
Binary first. Okay, binary first.
Okay.
Oh, still the same result. That means the solution is stable, right? Yeah. Not depending on initial condition. Okay. What will happen if you put without binary linear programming, but you start with 0, 0?
Oh, start with 0, 0. Linear programming. So yes. I will
just delete those two.
Delete. Okay.
Oh, still a 0.5. Same result. So yeah, the result is not the same, right? Between linear programming and binary, okay? But between integer, in this case, with the binary is the same.
Okay, and this one is IP.
IP. Yeah. There are two types of IP. Yeah? One is integer, the other one is binary. Yeah. So in this case, the same. Integer integer and also binary, also the same in this example. Right.
IP
IP
the binary.
binary. Yes.
Okay.
Okay. Very good. Very good. Okay. So with this, do you have any question about integer programming? Easy, right?
For now, it's clear.
It's clear. Very good.
Yeah.
Right. So basically, integer programming is just linear programming, but the values are integer.
Integer. Oh.
Okay. So we can go to the next topic. With this knapsack, isn't it? Knapsack. Okay. I forgot. I think we do have discussed this last time. This is also example of integer programming. Okay. But the problem is called knapsack problem. Do you remember or not? Knapsack problem. So this one, you remember this? A wealthy individual, institutional investor have certain amount of C. Okay, available when C want to put a profitable business project. As the basis of her decision, she compiled a long list of possible investment, including every investment that required the amount of W and the expected net return V. Okay, over, for example, 1 year or 1 month. Okay, the risk is implicit in the net return, right? So now suppose you have $10,000, okay, for your capital, and these are the possible investment of this month. Okay, so investment A, cost per stock is 120, and you expect, based on your analysis, you expect to get 1225, okay, and so on. So the question is, how many stock will you buy for investment stock? So my question to you, can you solve this problem or not? Oh, number one first, can you formulate this? Can you put the optimization formulation of this kind of problem?
Optimization.
Okay, you can write down the maximize or minimize. And what are the decision variables, and then objective function, and then the constraint. Okay.
You want to maximize.
You want to maximize. Okay.
Yeah.
Okay. This problem is in the slide of Knapsack, which is also in Lentera. What do you maximize? How many variables? What is the objective function, and what is the constraint?
Okay. Yeah. You have investment A, B, C, D, E. Cost is how many stocks should we want its investment? So we have 3 variables.
3 variables?
What? Oh, 2.
Two. Is it 2 variables or 5 variables? What are the 2 variables?
The cost. Oh, we need to make it for every investment, right? Yes, so ABC. Because A, wait, let's see. This one X1, X2, X2. You have the capital investment. So, so it's A, B, C, D. Ah, so we have 5, right? Yeah.
Yeah, 5 variables.
Yeah, so A, B, C, D, E
Yeah.
is must be less than or equal to 10,000. The investment.
Yes, if you so correct.
Yeah. Let me
Okay, try to formulate first. Okay, you need to formulate the maximize what. So you define
uh,
x a x b, right?
so the capital for the
The
capital
capital is 10,000.
XA XB plus XC plus XD
Plus
plus
e.
XB.
Mm.
This
Uh,
one must be equal to 1,000, right?
no. Uh, the cost multiplied by that, right? So
Ah, yeah. The invest. Yeah, yeah.
okay,
So the
x1
cost.
x1 is the amount of stock of A. Yeah, for
Mm-hmm.
XA is the amount of stock of A.
So
A
we
little bit
need
tricky, right?
to.
So
Yeah.
so let's
Mm-hmm.
define it.
So we need
X1 XA you type that XA equal XA is what you define is the number of stocks A,
is
the number of
number of.
stocks investment A, right? Or stock A, yeah.
Oh,
Okay. And so on, yeah. Stock
yeah.
XP and so on is the same thing, right?
Mm-hmm.
Okay, that is the one that you want to know. So for each
Yeah.
stock, right, you have the cost, you also have the potential profit in this case, right?
Number of stocks A. So we need to multiply it by the cost. So let's see. So here, let's say the cost is Y. So
The cost is already given there 120, 90, 175.
oh, we just
Yes,
DXA
90,
190
correct,
and
175,
175
and then
300.
100, and then 225. Okay, that one should be less than or equal, right?
Less than,
Correct? Less
than.
than or equal. So, meaning the total cost can be less than 10,000, but maximum 10,000.
Mhm.
Okay? And
And
then, what do you want to maximize? So, you know it's less than and equal, this is constraint, right? That's clear.
mhm.
So, what do you want to maximize? Of course, what you want to maximize is your profit, right?
Yes,
So, what is the profit? or the return, the max expected return in this case, right? So what is the objective, the Z?
Z. We want to maximize the profit.
Mm-hmm.
So
So,
maximize the Z.
okay, what is Z?
So
Z is
Z is the
the right side on the table.
the
Right?
expected return. Yeah.
Correct, correct. So that one is 100, 1225,
It's
1225 multiplied by
XA.
XA plus
Yeah. Plus multiplied by
XP
XP
and so on.
plus profit. XP and then 2000
XC
XC and
plus
then
35
3
XT
XT
plus
and then 2 3 4 0
0
XT.
XT. Oh, then easy. Once you can formulate this, then easy, right?
Yeah.
Because this is stock, you cannot use half. Okay, so this must be integer.
Mm.
Hmm. Okay, can you solve this?
So wait, the constraint. What is the constraint? This one, right? The constraint.
Well, let's continue later. 1 o'clock is okay.
Okay. Yeah.
Okay. Okay.
Okay. Okay. See
Okay.
you, sir.
See you
Yeah.
at 1.
Okay.
Okay, we continue this.
Okay.
Okay, so let's continue with the knapsack problem.
Okay. I will share my screen.
Sure.
Yes.
Yes. Wow. Okay. So correct. Yeah. And then now you try to solve it. Yeah. Solving it is rather easy, right? Once you can create that formulation, okay, solving it is just plug into numbers and formulas. Okay, try to solve it.
Like using
Yeah, so you can just, again, you put XA or you can put it
X.
there.
Okay. So here
Yeah, okay.
XA
A,
and then
XA,
XP
XC,
XC XC XT XE
okay.
and then there is
D, okay.
constraint. The constraint.
Okay, there is
Let
only
me see. The Z is
1, 2,
16 and then 19.
I think that is, okay, let's see. That is the constraint, right?
Ah, yeah. Wait, let me change
That is okay, it's okay.
here.
Just after finish, you can move it down.
Yeah.
300 multiplied by XT,
XT
and then
plus
225
225.
multiplied by XE.
Okay.
Okay, you can just move it down. Right.
That's correct.
Okay, good. And then
And now, what is it? So, here is 25 and then this is then for this is 2000.
35.
Okay.
Okay. Okay, and then put the color yellow so that you can know which one you want to change.
Okay, so this so
Maximize G. Okay, variable is the yellow. All of that. Okay, correct. And then the constraint is that one. Less than equal what? 10,000. Okay. Okay. And then add one more constraint because they must be integer. Okay. So all of that must be integer. Okay, finish. And you can solve. Oh, you got solution. Yes. So you see here is not exactly 10,000. It's just 9,900. But why I can get 10,000? My, I don't know. Can you check the slide? Actually, I can get 10,000. There. Next. There. Maybe there is something. 11,000 or 116,500. What is your result? Wow, very big. Your result is bigger. Maybe, okay. I know why. Okay. So I think there is a different in numbers. I think the first one is 1225. Oh yeah, 1225, correct.
yeah.
In your case, correct, 1225, 880, 2000, 35 to 350, correct. How about the constraint?
This one is H1 2.
Okay. 2, 3, 4, 5, 6. Okay, shifted, that's why.
Yes. Yeah. Can you see my screen now?
Not yet.
Not.
Oh, that.
I have fixed it and I got the
Same result, right?
10,000.
Yes, 10,000.
Yeah.
So you get also the 6. Oh, you get different C and D for my case, but the result is the same. The objective value is the same. In your case, 31 and oh yeah, it's exactly the same.
4.
Exactly the same. 31 and 4, correct, correct. Okay, exactly the same then.
Mhm.
Okay. So
Okay.
uh,
It's
the way
uh,
I did,
near programming, right?
yeah, yeah, exactly the same as
Yeah.
integer programming. Okay. Knapsack is basically
Okay.
integer programming. Uh, the way I did, I don't uh, put the formula. So all I did is something like this. I just put the uh, numbers. Can you see it?
Mm.
Okay, I just put the numbers there. And then because they are actually very simple formula, right? So we can just multiply. So W times X and then V times X. W is the cost, V is the net return.
Ah.
Okay. And then after that, we can just simply use like this. So because they are array, so you can just put together, right?
Okay.
So because they are array, so you can just put two constraints. One is the total cost less than the budget, and then they are integer.
Mm.
And yeah, the result is the same. Right. So uh, knapsack problem happen in many things in our life, right? So this is an example of the original knapsack. A hiker packed his knapsack for his mountain tour, and then he has an object to bring. Each object has certain weight, W, which give him certain profit, comfort, utility, benefit of V. Okay, the limit of his knapsack is C. So then you can formulate knapsack problem as linear programming, something like this. Right? So given VI, W, V is like the profit, okay? W is like the cost, and then the capacity. Then you can find the X. My question to you, what kind of other problems you can formulate as knapsack? Can you
Mm.
think of other problems that you can actually solve as knapsack? Oh, one more thing. How about your project? Are you going to do it together with Joy or you want to do it separately?
I think we're going to do it separately, so
Separately.
individually.
Okay, individual then.
Yeah.
On March 7 or March 8, right? March 8, you need to present your project. And March 7, you need to submit your short report, yeah, about what are you going to do
Mm.
in Lentera.
Okay.
And next week
Oh,
uh, is not holiday.
yes.
They change the holiday, so next week is not holiday because the Ministry of Religion changed from 1st March to 28th. So Monday become holiday, Tuesday will not holiday. So we have class next week. Okay. Can you think of other problem that you can set up as knapsack problem? Can you think of other problem? Hmm. Can you think of other problem which you can formulate as knapsack problem? So imagine something that has
Mm.
cost and has uh, profit or benefit, okay? Cost and benefit, right? And then they are in linear term. in that way, if you can think of that way, you can actually solve, you can actually create your project, right?
There is cost and then what cost?
Benefit. There must be some benefit.
Cost benefit.
So Knapsack problem has three requirements. One, you have cost, right? The second, you have some benefit or value.
Cost benefit.
Okay? And then, of course, you have the limitation of the cost. Okay? You can think of that. Okay? Think of other problem that there is a cost. Yeah. It's okay if you cannot think it now, but probably on
How about the wait the like the package for airplane? Can we do that? Knapsack, like
what?
the luggage.
Yeah, that's the luggage for airplane. Oh, so that is
Can we do that?
can
No.
can.
Yeah. We
But
can do
at
that,
the
right?
same time, that is difficult to find the benefit,
Yeah.
right? It's difficult to find the benefit. So, of course, you can also do that, right?
Yeah, the benefit we can
So you need to. So here, I give example in the slide, right, about the airplane. In this, where is that? So here, the airplane, right? The dispatcher of cargo airline decided to uh, has to decide how to load package into particular plane. So in one airplane there is a capacity, right? So and then each packet have weight, and then every plane have maximum capacity, correct? Now, depending on a particular long-term arrangement with every customer, now you can there's a rate per weight unit charge, right? So the profit is to put corresponding package on the plane. Okay, it's actually not proportional to the weight, but you can also set that. So you can set certain profit that the company will, or you can charge that as a profit. Another example is production. This is example, say a sawmill, to cut the wood, right? They need to cut into shorter piece, right? From one tall tree, they need to cut into smaller pieces. So the pieces must, however, be cut into some predefined standard length, right? Because usually the house have certain length. So the standard length is WI. Okay? There are a few standard length. So for example, 3 meter, 4 meter, 5 meter, right? And then each length has certain different selling price. Okay? So then given the one lock, so you need to optimize how many pieces for each length you should cut. So these are the example of knapsack. But you can also think of other example.
Okay.
Okay. So uh, the cost not necessarily represent money. Okay. For example, the cost represent your time, your effort, okay, your energy to to do something, right? And then the benefit probably represent something that you value, okay? Not necessarily in terms of money, but for example, you value in terms of something else, or utility. Okay? So that also possible. Okay? So the most important is the formulation will be similar to this. Okay. Okay. So then I have. So once we discuss about knapsack, now let's discuss the TSP. This is also TSP is also one of the integer programming example of problem, right? We discussed last meeting. What is TSP? So traveling salesman problem. Yes, you want to find the shortest route, right? By visiting each city in n number of city exactly once. Okay. Hmm. I remember you did this last semester. Mm-hmm. You remember?
Yeah.
Yeah. So using Excel also, right?
Yes.
Yes. So what did you do?
Wait. No, the last year. We first we define the destination perfect.
Okay. You want to tell me? Share. You want to share your screen or?
Oh wait. Okay. Um, okay. So first, like the one that we do is like the city or something.
Okay. Let's try that. Okay. Let's try that. I have a
Say
city like this. Can you solve this city? The solution is here. This example of city. Can you solve this? Can I
which one?
show you? This one. This one. This slide is also in Rentera. You can download.
Okay. I will open this.
So we have how many cities? Four cities. Because
Okay.
it's four, I can calculate
So,
by hand.
uh-huh.
Mm-hmm.
Itu is travel salesman background.
You want to share your screen? You can start from any city as long as they form a cycle, and then you visit only once for each city. Okay. So D to A is 20.
And
And D to B is 25.
to 630.
D to C is 30. Right. And the matrix distance must be symmetric. Yeah? Symmetric matrix.
Oh yeah. This one. Okay, and then we do like we order it, right? Like
Yeah. So we need to find the order. Maybe we need to give name A, B, C, D.
give into what, sir?
Okay. 1, 2, 3, 4 is what?
The order.
Yeah. Okay.
Like what should you visit first, right?
Then
Okay, so order. Yes. And then distance, right?
correct.
And then
Then
after the distance, the that I forget the order and then the distance, and then we
and
want
the
to
city.
find the
City.
oh yeah.
Okay, city is ABCD.
Okay, so if we
And that
want
one you
to
can use index.
for the city.
Yeah, index of the city. The city is just AB, column A, A, B, C, D, A, B, C, D. Right, comma the order. A8. Yes. Okay. Close it. Okay. And no,
Oh, I
the
need
city you
to.
need to put a dollar sign. Okay.
Okay.
Okay. Perfect. Now
Plus.
you get the distance again. You use the index.
So this one, right?
No, no. Uh, do you want to put the distance as a distance, meaning you want to give name? For example,
Yeah.
E2 until E5, you give name as distance or
Oh,
M distance. Yes, that one you give name. So
this one.
distance. Enter. Okay, and then
So
now you want to get the
index,
index of the distance, correct? Comma.
and then comma the order, the city.
The order of the city is the last one before. So in that case, A11, comma A8, comma A8. Right? Okay, that close that, close parenthesis. And then the second one, the same, but the city is different.
Just let me copy it
No, you cannot
first.
copy. Uh, the second,
Um,
the second one you need to get from uh, index of distance again.
mhm.
Okay, and then
This was
comma the earlier
A.
A8 and A9, correct? Yes, A8, not A8, not 11. Yes, correct. That one you can copy. The
Oh,
B9 you can copy down. Okay. Uh, why?
and
Because
then
the
using
first one copy from the bottom, right? Because it's a cycle,
mm,
right? And then you
oh
can,
yeah.
yeah.
Yeah. Then we can use the solver,
Then
right?
you take the sum of the distance,
So,
sum of the distance. Okay, that is the objective function, the z. Yeah, the total is the z. Okay, so what to do?
we want to do the using the solver
Mm-hmm.
to let's show the objective.
The objective is the total distance. Very good.
And
And
then we
then
need to
uh,
maximize, like,
you know
to minimize
you
the
want to
distance.
minimize. Okay? You want to
Yeah,
minimize.
to max the
Minimize the
distance,
total
and
distance
then
and
we
then
take the order.
order. Yes, correct. And
And then
then constraint. This is the most important part. The constant is what?
the constraint is, wait, the order, and then the distance, right?
The order must be all different.
So,
So the order,
using the div.
yes,
So this
that is the order. Right.
one.
And click OK.
Okay.
So if you solve
Yes.
this, I don't think you can solve this using. Is it possible to solve this? Try. Oh, you found the solution. Okay, in this case, probably possible. So you get 80. Is it correct, the result? Is the correct? Is the result correct? A B. Oh yeah, A B D C. Correct. A B D C.
Yeah.
Yeah. If you cannot solve using the CSD non-linear, okay, you can solve using genetic programming. So inside solver, can you check the solver?
This one.
Yes, there is.
No.
Yes, evolutionary. So you can solve using evolutionary. So in that case, you probably need to change the option. Okay, so the mutation rate you change to 0.5. So that,
What is the mutation rate actually?
mutation rate means you change the, it's just a parameter to 0.5, not 0.05, 0.5.
Oh,
Okay, very big mutation rate, meaning that it will use random. Uh, I can teach you genetic programming, genetic algorithm. I think I already put that in the in Lentera. You can check. Okay, so you can see here there is a mutation rate, there is a population size. And, okay, you can click OK. Okay,
okay. And then
okay,
so.
and yeah, and then you solve. Yeah, for this case, you get the same result.
The same, yeah.
Uh, okay, so let's go back to TSP first. Okay, you want to check in Lentera if you can see the genetic algorithm is already there.
Okay. Genetic algorithm.
Is it there already?
I will use
Lentera.
zero something.
The last one, the last one.
Ah, yeah.
Yeah, you
Genetic
got that, right?
algorithm.
So there is slide on genetic algorithm before the final exam. If you want, we can change the
Yeah.
order, no problem. But there you can see, I think it's rather clear in that GA here.
Mhm.
So in this GA, I use Excel only. Again, so in this slide of GA, I use only Excel. So yeah, you can try that if you want. So if you look at that, there is mutation, crossover, inversion, or reordering. So those are the operator inside the genetic algorithm. Okay. Yeah, it's more complete than what Excel software is doing. Okay. So okay. So let's come back to traveling salesman first. Okay.
Yeah.
So, and if you need something else, so you tell me, we can accommodate you for your need. Okay. Traffic salesman is rather important for industrial engineering because many problems is actually similar to this traffic salesman. So you have solved this, right, earlier? Is the answer correct, 80?
Yes.
Yes. So
Yeah, I got it.
exactly 80. Yeah. So this is called Hamiltonian cycle. Yeah, it's exactly the same. So Hamiltonian cycle, yeah, is a circuit to visit its node, okay,
Mhm.
exactly once. So there is another cycle which is also famous called Eulerian cycle. What is this? It will visit its link exactly once. Can you distinguish Hamiltonian cycle and Eulerian cycle? Yeah. So TSP is basically the shortest route of Hamiltonian cycle.
Mm.
Now there is another problem called Chinese postman problem. So similar to TSP, okay, but the difference is this is actually optimization or shortest route of Eulerian cycle. What is Eulerian cycle again? Okay.
Yeah.
There are two unique cycle, or no, not unique. There are two type of cycle that is quite unique in terms of the technique. Okay, one is called Hamiltonian cycle. Hamiltonian cycle will visit its node, its vertex is node, right? Its node exactly once. Okay? The other one is
Mhm.
uh, to visit its link, its arrow exactly once. So if its node is exactly one, that is called Hamiltonian cycle. If its link visited exactly once, that is called Eulerian cycle. Okay.
Mhm.
TSP is the optimization of Hamiltonian cycle, shortest route. Chinese postman problem is uh, the shortest route, optimization of Eulerian cycle. So Chinese postman problem has been solved by this algorithm, Flory algorithm, right? So, but Hamiltonian cycle optimization is not easy. Okay, uh, in fact, there is no real algorithm to solve this until now. So the brute force approach is something like this, right? So you consider CTA in the node as a starting and endpoint, and then you generate all the permutation of the cities, right? And then you calculate the cost of every permutation. So in that case,
Mhm.
the complexity is factorial of n factorial, O n factorial. So this is called NP-hard problem. Okay, and if you want to use Python to solve this, you can check this website. Okay, and I copy and paste from that website, so you can see here. Maybe I change a little bit anyway. So you can try to run this in Python. Yeah, copy and paste, and then run this in Python. For small number of cities, this is okay. Okay? But if you have many, for example, more than 20, it will take a long, long time. So, because this is the naive implementation, mean you use factorial. Yeah? Okay. So there are many other methods to solve the TSP. So one is to use dynamic programming. Next meeting, our next slide, we can discuss about dynamic programming. Okay. So there is an algorithm called HELCARP, which use dynamic programming. Again, still 2 exponent n, right? That means still exponential. Okay, not factorial, but still exponential. So TSP has been solved by by many people. So these are the example of links that probably useful for you. Uh, please check this link, TSP competition. Okay, every year there is a competition on travel salesman program. Mm, worldwidely, meaning we still don't know what is the best solution yet. That's why they make it competition. So if you can win this competition, you will be famous worldwidely, not just in Indonesia. Okay, so just simple problem, right? TSP, right? And you learn that already. Yeah, yeah, you can solve it only a few notes you can solve. But uh, yeah, this is already done. So the formal definition of PSP is something like this. So given the graph G, okay, the graph is consists of vertex and edges. So that means V is the vertex. Okay, you have n vertex that represent the cities, right? The edges here represent the link. Okay, and given the D, the cost associated with the edges, okay, the TSP problem is to find the minimal cost of the closed tour, okay, that visit each city once. Right. Important is to formulate, right? In OR, the most important is to formulate. So this is the formulation by Danzig, okay, in 1954. You can download this paper if you want. Do you know who is Danzig? Oh, you don't know. You are in OR, you need to know. Huh? This man is the one that actually creating the linear programming. Okay. Okay. So Danzig is the one that created linear programming. So you see that linear programming is actually created during the World War, Second World War.
Yeah.
Okay. And they, uh, of course, Danzig is one of them who solved the war using optimization. Okay. During the World War II, okay, they use optimization for logistic, for ballistic, and so on. Okay, so so TSP as linear programming, integer programming. You can see this is like the cost times x, right? So x here is what? Binary. Yeah. Look at the last constraint there. Okay, the last constraint, the x is actually binary. Okay, and of course, the sum of x, xij is from I to j, right? So the sum of xij to the, what is that? The j, okay, and to the I must be exactly 1. What does that mean? Okay, the constraint, that is this one, mean to go constraint, right? Meaning that after visiting a city I, okay, the salesman must visit only one next city. Okay, must exit its vertex, exit, yeah, its node exactly once. That's the meaning of this constraint. What is the second constraint there? The second constraint is sum of I of xij equal 1. Okay, so the second constraint, that means coming from constraint. Yeah? So when visit a city J, the salesman must come only from one city I. So both sides. This constraint is to guarantee that they have only all difference available. Remember, this is 1954, okay? All different does not exist yet at that time. Okay? So inside the all different is basically something like this. Okay. So, and then what is the third constraint about? The third constraint, you have this, yeah? Sigma of x comma j, that means both of them, okay, must be less than the number of s. Okay? S is the number between 2 until n minus 2. N is the number of cities. So the third constraint is called subtour elimination. This is the one that creates all difference. Okay, that it will create to ensure that the tour is actually fully connected without sub tour, with not branching. Okay, so to ensure that no proper subset S can form a subtour, then they limit that subtour. Okay, the tour means the cycle. There is no sub-cycle. Right? So that means all difference. Okay, of course, the last one is just simple. This is just integer constraint. Okay, so again, yeah, in OR, especially during linear programming, integer programming, the most important part is this one, to create the uh, optimization formula. Okay, so the objective function is the distance, right? So the cost multiplied. The cost is basically Euclidean distance. If you know the coordinate, you can just get the coordinate of the city, right, based on Euclidean distance. Okay, what else? Oh, after that is easy. You already did this, yeah? Solving. Right, so the total ordering of the city n factorial, n minus 1 factorial, you already did this. What else? Oh, if you want, you can try. Okay, what happens if your distance matrix is actually big? Okay, maybe you can try in Python so that you can see how long you will take to solve that problem. Okay, so now you already know TSP, you already solved it a while ago, right? So the next question is how to apply, right? If you have if you know some knowledge, okay, it's not so useful if you don't know how to apply, right? So these are the example of problems, okay, which is similar to TSP. Okay, one is called vehicle routing problems. Say you have delivery, right? Delivery driver need to make a certain number of stops. Then you need to know which one first you need to put so that you will minimize the time to travel. And this has been applied in many logistic company. Say, for example, you are creating like Grab. I don't think Grab will give you this optimization routing, right? Say to the Grab driver, there is no optimization yet. They just go one place and then come back, right? But if you are delivering food, for example, is it possible to create the optimization for that, and then probably you can sell this optimization program, right? And
Yeah.
in fact, this have been used in many European companies for logistic company, okay? And uh, they reported that they save a lot of million of euros, yeah? Because they use this kind of optimization. Imagine if you can, instead of only 2 stops per day, now suddenly you can make 20 stops per day. That means 10 times of your profit, right?
Yeah.
Something like that. Okay, that's a lot, because you minimize directly. Yeah. So TSP can be used in sequencing. Okay, for example, job scheduling, right? So in job scheduling, you have 10 job and then each job have time, right? Okay. And the question is which one first? So sequencing. Okay. Which one first? Okay. And another example that is a very famous example is a robot. Say in the chip company, okay, there is a board, a printing circuit board that they need to make hole. For example, so there is a hand robot that can create a hole, but the question is how to optimize the hand robot. Okay, so which order first? So these are the example of TSP. Oh, garbage collection problem. I don't think garbage collection uh, has been optimized yet in Surabaya, for example. So, yeah, this can be a topic for thesis, how to optimize the garbage collection, okay, in one city. Okay. Not just one place, but one city, right? Because this is interesting problem, yeah. So you can try this. Uh, I think you did this right last time.
Yeah.
Yeah, okay, okay. If you did this, okay, forget about it. So, uh, yeah, that's all for traveling salesman. Is there any question or you want to comment something?
Mm. So like, what is the requirement of the problem that can be solved using the travel salesman problem?
Very good question. So that means there is a sequence, and that sequence will
Sequence.
create a loop. Okay, so the problem of TSP is there is a sequence that create a loop. Okay, and then each of this sequence, the link, okay, there is a cost. So the cost here is generalized cost. When you hear the word cost, you listen to cost mean what? Cost mean actual money, cost mean time, cost mean effort, right? Cost is something that you hate. Okay? Cost mean energy that you need to put out, something that you don't like. So that's minimizing. Okay. And the goal is to find the sequence that actually minimize the cost. But you need to visit all. That means the assignment must be for all. That is the requirement for a problem to be TSP. So if you can think of other problem that you can solve using TSP, that would be great. And sometimes you want to combine, okay, one method with other method to create something new. Say you know already, right? Oh, I know TSP, I know Knapsack, for example. Can you combine the TSP and Knapsack into something else? Anyway, both of them have cost, right? But one have
Yeah.
profit, the other one have no profit. TSP has no profit, but Knapsack has profit there. I mean, the benefit is there in the formula. So then you probably want to combine. I don't know. Okay, creatively we can actually combine many methods together. Okay, and then you will create something new. Uh, okay, good. Oh, it's almost the time. So next meeting we will discuss dynamic programming. Okay, it's just 3 minutes. So the DP. Did we discuss dynamic programming in other courses or no?
I think no, not yet.
No, not yet. Okay. So this is new for this class. TSP we discussed, Knapsack we discussed, linear programming we discussed. Integer is new, but Almi is closely the same as LP, right? So
Yeah.
yeah. So from DP is new that I hope it's interesting for you. And after that, we go to the real decision making problem. Yeah? So decision analysis is. Oh, did you learn decision analysis in other courses?
Decision analysis. No, I guess.
No. Okay. So this one is the actual course for decision analysis. Huh? You can also read in the textbook that we put in the course syllabus. Okay.
Okay.
Yeah, they are very interesting. Actually, very very interesting. In fact, later on we will discuss game theory, right? Okay.
Yeah.
And yeah. So you can check the movie of Beautiful Mind. Okay, maybe you can find in YouTube or something. Okay, Beautiful Mind
Beautiful.
about NAS. Okay. Or you search in Google Beautiful Mind NAS. Okay. That is actually about game theory. Yeah? We have NAS equilibrium. Okay, they even make it into movie.
Oh.
Oh, okay. So that you can get interest. Oh, this is a very nice course, right? In fact, so many Nobel Prize winner. Okay, Nas is get Nobel Prize also. Okay, other Salesman get Nobel Prize, Harsani get Nobel Prize. Okay, all of these are about game theory, decision making. Okay, Arrow also get Nobel Prize in group decision making. See, so many people get Nobel Prize in decision making, meaning that this is really important. Okay. Okay, so see you next meeting. Next Tuesday, we have class.
Yeah. Okay.
Okay, so
Okay.
no assignment. But
Okay.
last week assignment, please submit.
Yeah. Yeah. Okay. Okay.
Okay,
Thank you,
bye bye.
sir.
Bye bye.